Looks like we're live. Hello everyone and welcome to yet another Azusin session. How about that? I bet you didn't expect that shit to happen. Here we go. Let's make a little bit of an announcement on our Discord server and officially start the stream. So I'm gonna do red car, sure, live on Twitch, and today we continue developing Knock, which is basically like a very small programming language designed for processing mathematical expressions. That's what it is. And let's give the link to the channel where we're streaming, and I'm gonna ping everyone who's interested in being pinged. And there we go. The stream hopefully has officially started. Has it started? I don't know. So do we drop frames? We don't drop the frames. Dara Dust, hello, hello, welcome, welcome, welcome. Yeah, so we're going to continue developing this language, and I've made a little bit of a progress off screen. Specifically, I implemented binary operations, so I think it's going to be very, very interesting. So you can find the source code of this entire thing here, and for people who's watching on YouTube, I'm going to put that in the description, of course. One day I'm going to upload all of these episodes to YouTube. Trust me, once I find motivation to do so, I'm gonna definitely do that. Alduck, thank you so much for 2 months of tier 1 subscription. Hope you have a good stream. Thank you so much, and hope you enjoy watching this stream. All right, so let me take a look at the latest changes. So I hope I don't have anything here, so let's actually fetch the latest changes. And also merge origin master. Okay, there we go. So, and now I'm gonna start the knock, right? So I'm gonna wrap it with RL wrap. And as already mentioned, one of the important things that I introduced off screen, actually I introduced it today, is binary operators, right? So there is a bunch of predefined binary operators. They don't really mean anything, but you can use them as patterns. For instance, you can do shape, and you used to do just like f of a and b to define some sort of like a function application, right? And then you would be able to apply some rules, like apply like all rule, and you would say, okay, so match f, a and b, and replace it with g of b of a. And it would actually replace f with g, and it will take the first argument and the second argument and swap them. So as you can see, the point of the language is to actually match these sort of expressions and replace them with something else, capturing the variables and stuff like that. So this is basically an entire language based on pattern matching, right? So, and recently I introduced binary operators, so you can do stuff like this, right? So this is a legit expression, and you can apply different rules to that expression. For instance, you can have a rule a plus b is going to be equal to b plus a, and it will actually swap these things around. So you have a bunch of predefined operators. In fact, I think you have 5 of them, right? So addition, subtraction, multiplication, division, and power, right? So, and they have their own classical precedence, right? So the highest precedence is power, a little bit lower precedence is multiplication and division, and the lowest precedence is plus and minus. So apart from the precedence, the language does not assume anything about these operators, like literally anything. So you can define whatever you want, you can define any patterns you want, and it will just accept it. So basically, operator is just a functor, right? It's just a shape that you can pattern match and sort of demonstrate something, right? So while you're doing mathematical doodling around. So that's basically what it is. And you can use that to define different like clauses and just like maybe prove something for yourself. And that's precisely what we're gonna do today. So we got a couple of subscriptions. Thank you so much, Titoant, for 2 months of tier 1 subscription, actually Twitch Prime subscription. Knock it out. Yeah, haha, very funny. Thank you so much. And Morrigan++, Roost Gung. Thank you so much for 2 months of tier 1 subscription. Thank you, thank you, thank you. Are you checking whether I can read Cyrillic? All right, so let's actually try to, I don't know, demonstrate something with this language, right? Something actually interesting. You know what I'm talking about? So let me show you. So let's actually try to demonstrate that the square of the sum, right? So the square of the sum is equal to a squared plus 2 multiplied by a multiplied by b plus b squared. Can we, through a sequence of transformations, like defining rules and stuff like that, demonstrate, not proof, because in Nock you don't really prove anything, because this is not a coq, right? So coq is designed to actually be a proof assistance to like prove certain things. We're a little bit relaxed on that. We're just allow you to transform expressions to whatever you want, so we're not really proving anything, we're rather demonstrating something. And once you demonstrate something, you can move to coq to actually write like a proper proof for that. That's why I called Nock not coq. It's not really coq, it's not meant to replace it, it's not meant to even compete with it, it's just like its own thing to doodle around. Right, can we demonstrate that a plus b squared is equal to that? Like a really famous formula. You know what I mean? Okay, so let's give it a try. Let's try to shape it. One of the obvious things is that square of anything is basically that thing multiplied by itself. Can anyone agree on that? Right, we can sort of define this rule. Right, let's actually call this rule a square. Right, square of anything is basically like anything multiplied by itself. We can define that rule and then we can say, okay, apply that rule to all of the matches that you encounter. Okay, and this is what we got. Right, we had this expression, we defined this rule, we applied that rule, and this is what we got. Isn't that cool? I think it's pretty cool. So, the next thing we probably need in here is some sort of a distribution law, right? So essentially, when you multiply a by b plus c, we know that a is that it's equal to a multiplied by b plus a multiplied by c, right? So this is some sort of a distribution over multiplication and addition, right? So that's what it is. It's a distribution over multiplication and addition. So we can define this rule and we can try to apply this rule to all of the matches that we encounter. There's only one match, but we're going to apply it anyway. And this is what we got. So what's interesting is that we can try to apply it again, right? Because we have a couple of situations in here where the distribution law actually applies. But it's not going to work because that distribution law is defined over a and then the parentheses. So you sort of need like a second one, or you need a commutativity rule for multiplication. I probably pronounced it incorrectly, commutativity or something like that. So essentially a multiplied by b is equal to b multiplied by a, right? So we're gonna call this rule multiplication commutativity, right? So this is basically the rule, and we're gonna apply this rule to all of the matches that we encounter, and there you go. We basically swapped around both of these two things, right? So and now we can apply the distribution multiplication rule, right? So basically apply all, and as you can see, this is what we got. So yeah, but basically the point of this entire language is to just start shaping the expression, define a bunch of rules, and just apply those rules sequentially, getting the expression somewhere, right? So it's not meant to prove anything, it's just like doodling around, right? This is something that you could do with a pen and paper, right? So we can do that with a pen and paper. But with the computer, it's a little bit easier. So what we have in here is very interesting. So as you can see, I already mentioned that Nock doesn't know anything about addition, subtraction, multiplication, division, and power, right? It doesn't really assume anything about them. It doesn't know that you can also have, what is it called? Distribution, commutativity. It doesn't know that plus operation is associative. Right, it doesn't know anything about that, right? And this is basically the parentheses that it happened to have after a sequence of transformations, right? So, right, it doesn't really mean anything for coq. But we know that a plus b plus c is equal a plus b plus c. we do know that, right? Because it's a basically, I keep forgetting, distribution associativity, right? So it's a sum associativity. And let's actually define a rule sum as soc, right? So, and let's try to apply this thing not to all of them, right? We don't want to apply it to all of them. I think we want to apply it only to the first match. And the first match in here is the one that matches this and this. So, and you can actually say that you want to apply it to the match number 0 because we actually count them starting from 0 because we're programmers, right? So let's actually apply it to the 0th one and boom, there you go. So we basically moved parentheses from here to here, essentially. You can see how we transform this entire thing. The next thing we want to do, I think we want to move the parentheses to here, between these two things. But unfortunately, we don't have a corresponding rule for that. So we have this rule, but we need a rule that is swapped around. So right now you cannot really take a rule and swap it around. You actually have to define a separate rule, unfortunately. And this is something that we're going to fix in the future. Let's actually define some soc1. And here we're going to do a plus b plus c equal to a plus b plus c. And this time we're going to apply a soc1. Right, hopefully it will be applied in the correct place. No, it was not applied in the correct place. We can always undo the application of this entire thing and say, okay, apply it to the once match. And there you go. So this is what we have in here. So we basically isolated sum of two equal things. So another thing we want to do, we want to probably make b multiplied by a to be equal to a multiplied by b. And I think we already have a rule for that. We have multiplication commutativity. So basically we can apply mul_com, but we have to apply it to I think we have to apply it to the second one. And as you can see, there we go. We actually transform it and now it's the same. And obviously we have a very interesting rule. We have a plus a equal to a. Let's actually apply it to this specific thing in here. So it's going to be rule, and how can we're going to call it double sum, right? So let's actually call it double sum, and let's apply it to the first match of the double sum. I think it's the only match that can happen in here, and there you go, we've got this thing. So another interesting thing is that we already kind of have the definition of square, but only in one direction. Now we need a definition of square in a different direction. Let's actually put it in here. So it's going to be a and squared, and we're going to call it square 1. And let's apply the square 1 rule to all of these things. And as you can see, we demonstrated that a plus b squared is actually equal to that given the rules, given the axioms that we defined in here. And we can also say done, right? There we go. So that's the essence of Nock. That's basically the programming language that I was trying to develop, right? So it allows you to define rules, and through the process of shaping, it allows you to apply those rules and demonstrate something. So it's not really a proof. I'm not trying to make a proof system or proof assistant. I'm just making a very simple like application that allows you to doodle around. So yeah. George Joyce, thank you so much for subscription. Christoph Eat, thank you so much for the rate with 30 tabs. Thank you, thank you, thank you. Yeah, that's basically what it is. What's interesting is that this is an interactive system, right? But you can actually save all of that to a file. Let's try to do that. I'm gonna just like select everything in here, and I'm gonna quit it. And let's create a file, square of sum. Right, so this is gonna be this, and I'm gonna put it in here, and I'm gonna save it. I really wanna open it with Emacs. So square of sum. Okay, so what do we want to have in here? So this is going to be the shape. I probably want to get rid of all of these things, right? So because it's just like an output, right? And on top of that, we probably want to get rid of this kind of stuff, right? And we want to move all of the rules up there. So let's actually find all of the rules. I'm going to put them here. cool. So there's also one undo, right? So I suppose you can quite easily just remove this entire thing and it's going to be fine. And yep, so essentially our proof has been put in a file, right? And you can just interpret that file and go through that proof yet again. So let me actually like assign this all that like so. We can also try to do something like this. Right, there we go. So it looks a little bit better. So as you can see, you have a bunch of rules and you have shaping. And shaping is essentially like sequentially applying those rules. You can sometimes apply rules to all of the matches, or you can apply the rule to a very specific match. And after that, you can just say, where am I actually? Cargo run square of sums, and it will print like basically the trace of that proof, sort of speak, right? So you can actually take your shaping and put it in a file, and then at any point interpret it and see how the expression was transformed, right? So that's basically what it is. So does anyone have any questions regarding the thing that I just shown? That's pretty cool. Yeah. So my ultimate goal is, in fact, make something like this work. Right. So this is just like a doodling around that I came up with a long time ago. I don't know, like a half of a year ago. And I always wanted to make a language that can kind of interpret that. The actual syntax is not in 100% correct, but it's pretty close to what I have right now. And only recently I decided, like, why not just like implement that language and see how it goes? So this thing does not really work yet, but this is basically a demonstration that a derivative of square is equal to 2 multiplied by x, right? You know, so basically you have a function f of x equal to x squared, and the derivatives of such function, right, derivative of f should be equal to multiplied by x, right? So you can demonstrate that by basically applying a sequence of different rules and stuff like that. And I always wanted to have like a thing that can show you that. I know that you can do that with Coq, but Coq is really bureaucratic in that sense, right? It's really finicky, and the documentation for Coq is extremely cryptic because it's filled with mathematical terms and stuff like that. But in reality, I just want to transform mathematical expressions, right? Like symbolic expressions. How hard could it be to just have rules that pattern match things and replace things in sub-expressions, right? You don't need a cryptic, you know, terms of Coq to just do that, right? You need just like an AST and yeah, just like apply and replace things. So yeah, basically, sounds more like Maple than Coq. I never tried Maple, unfortunately. What is a knock block? I don't understand what is a knock block. I'm sorry. What is knock file extension? It's basically a file that contains instructions of knock, the instructions that I just put in REPL in here. You can actually take all of these instructions and put them in the file and just interpret them, and it will understand that. Will there be a steady leap of rules? Of course, right? So we're going to have a standard library where we have all of these like axiomatic definitions, like sort of axiomatic, they're not really axiomatic, definitions like associativity, commutativity, and stuff like that for like sum, multiplication, and stuff like that. In the future, we're also going to have custom operators like in Haskell. Believe it or not. In Haskell, you can literally define any sequence of special characters, right, something like this, and declare it an operator. Interestingly enough, like, this will require a very interesting tokenizer, right? It will require a very interesting tokenizer. As soon as you define a new operator, the definition of the operator has to be used by the lexer to lex the code differently. So the definitions of operators should affect how you lex the rest of the code. It's really interesting, right? So imagine like in Haskell, I think in Haskell and many other functional languages, the semantical definitions semantical definitions affect how the language is lexed or tokenized. Imagine that. And we can try to implement something like that. Why not? I mean, it doesn't really sound that crazy. Right, so we have an execution context, and in the execution context, we have definitions of operators. We're going to have a definition of operators, and we can just pass that context to the Lexa, and Lexa can just use the information in the execution context to parse the rest of the things. It doesn't really sound that difficult to do, especially if we implement everything from scratch. And we, by the way, implement everything from scratch right now. So far, we're not using any third-party dependencies, any parser generators or anything like that. I parse everything by hands, manually. Right, so, and since I do everything by hands manually, like making such a crazy tokenizer doesn't really sound very difficult, because I can just do that, because I have control over everything. Right, so here's the entire Lexa, right? So this is the thing that just lexes everything, so different tokens, different kinds of tokens, it's just like 300 lines of code. And the parser, fn parse, the thing that parses the expression. So here are the things that parse the expression, right? And if you take a look at the TOML, there's no any third-party dependencies yet. We're gonna add some in the future, but right now there's not a single third-party dependency in this entire thing. Will there be a way for counting, like, for example, that's a very interesting question. I'm not sure if I understand what you mean. Just let me actually post this language here. Will there be a way for counting, like, for example, a multiplied by a equal n? So here's an interesting thing. That implies knowing about numbers, right? Nock knows nothing about numbers, believe it or not. It knows really nothing about numbers. It only knows about symbols, applications, and operators, right? So that's the only thing you have. You have just symbols, and symbol is just like in any sequence of characters, like you know, alphanumeric characters, just a name. And operator is one of the 5 predefined operators, and application is basically like taking any expression and applying it to any sequence of arguments, which can also be expressions, right? So this is application, right? So this is considered an application, right? You have only that. And you can do whatever you want with it. For instance, you can define piano numbers, and I already demonstrated how you can define piano numbers, right? So let me actually show you one more time, because it's rather interesting. So when I do something like 0 or 1 or 2, Nock does not interpret that as a number. As already said, it knows nothing about numbers. It interprets this entire thing as a symbol. For Nock, it is just a name. It is just a name, the same name as A, B, or C. It doesn't see any difference between A and 69. It's basically 2 different names, 2 different labels. But you can do whatever you want with them. Right, so let's actually do a real wrap, and I can show you. For instance, we can define piano numbers, right? Piano number is essentially a number. 0 is a piano number 0. 1 is s over another piano number, s over 0. 2 is going to be s over 0, and so on and so forth. So piano numbers is basically how many times you have a functor s over another piano number, right? And you can define a bunch of rules, right? So let's actually define rule 0, actually rule 1. And we can say that 1 is equal to s0, right? Let's define 2. 2 is basically 2 equal s over 1. And then 3 is s over 2. And then 4 is s over 3. There we go. We defined, you know, 5 numbers. We defined 0, 1, 2, 3, 4. Now we can do something with those numbers. For example, we can define an addition, right? So actually, let's actually define addition identity, meaning that 0 plus any number has to be equal to that number. So this is basically addition identity. Yet the language knows nothing about numbers. It also knows nothing about addition, right? For the language, these are just symbols. it doesn't know shit about like actual implications of those symbols. Another addition rule we can do is basically S of A plus B, right, is S of A plus B. That way you recursively define the addition, right? You recursively define the addition. There we go. So we have a bunch of rules, and these rules are enough to shape something like 3 plus 4. We're shaping 3 plus 4. What's going to happen? Okay, let's apply something like rule 4 to all of the entirety of expression, right? Now, as you can see, we have 3 plus S3. Now we can apply rule 3. And now we have that. We can apply rule 2 and then rule 1. There we go. So we sort of expanded symbols into actual piano numbers. Once you expanded symbols into actual piano numbers, you can start applying rule add to the actual piano numbers. And as you can see, it sort of shifts the addition towards 0. Every time you apply add, it shifts closer and closer to 0 until you have an opportunity to apply the addition identity. And you just add up 3 plus 4. If you count up 1, 2, 3, 4, 5, 6, 7, you have 7, which is exactly 3 plus 4. So it doesn't know anything about numbers. It doesn't know anything about numbers, but through the symbols, you can define basic arithmetics. It is a very low-level mathematical language. So it's like slightly higher than set theory, right? So you're starting like at the very bottom of the math. Like you don't have anything. You have to define even numbers yourself. So yeah, that's basically what this language is intended for. It's just like a symbolic math. If you want to define something, you can do that. You can play with that and so on and so forth. So does it make sense? Yeah, you literally construct the numbers, right? So it's a very specific language for very specific thing, right? To like, you know, mathematical doodles, so to speak. Mathematical doodles, so to speak. All right. So does anyone have any other questions? Is this chart encoding or something? It is really close to chart encoding. It's actually called piano numbers, or piano like axioms. If you've never heard about that, I really recommend to check it out. So it's basically trying to define like basic arithmetics. Usually basic arithmetic is just like taken for granted, but you can actually define it through more low-level things, just like I demonstrated. Right, the same way you can also define subtraction, multiplication and division, but I actually don't remember defining division with piano numbers, so I'm not quite sure. Once you define these piano numbers, you can actually prove the basic properties of addition, like commutativity, associativity, and like distribution. We actually, in the previous example, we made all of them sort of axioms, but through piano axioms, you can actually prove them as well. Right, so I really recommend to check this thing out. Valani, thank you so much for 10 months of tier 1 subscription. Thank you, thank you, thank you. All right, and Torrance51, thank you so much for tier 1 subscription. All right, so that's basically the progress on the language so far. And one of the things I wanted to do today is being able to apply reversed rules, right? If we take a look at the square of sum, right, we have these pairs of rules, right, which are basically the same, but they are reversed of each other. Right. So it would be nice if we had an ability to apply a rule, but then say, okay, apply that rule, but in reverse. Right. Essentially take its body and interpret it as a head, and take its head and interpret it as a body. Right. So that way we don't have to define two rules for the same thing. Right. We can just take the same rule and we can apply it directly or the other way around. You see what I mean? So in that way, we'll be able to get rid of these like duplicate rules, right? I think it's actually pretty convenient feature, and this is something that actually pops up in different sort of proofs that I was trying to do off screen. Like every time I want to try to do something off screen, quite often I need to apply already defined rule, but in reverse, right? So obviously you want to have something like that. All right. So speaking of infinite loops, we have different strategies, right? As you can see, you can apply a thing, and the first argument of the command apply is a strategy of the application of the rule. Right. So all will basically go through all of the matches, and every time it encounters a match, it applies the rule and continues the recursion in a different branch. A number is interpreted as nth match. Right. There's other strategies. For example, I think there's also deep strategy. Right. Yeah, this one's rather interesting. I think we even have an example for that. Inverting binary tree. So through expressions, you can actually define a binary tree. Look at that. So consider T function the following way. So you have a value in here, then you have a left subtree and a right subtree. That way, you can sort of like define a binary tree that looks like this. Right. That looks like this. Right. So this is the binary tree. And then if you define such rule where you just match the value left and right and replace it with f, x, right, left, and use the deep strategy, which after replacement actually goes deeper into the sub-expression, you will actually invert the binary tree. Let me actually show you. So if I try to interpret, so cargo run invert binary tree, so that's the result. All right, so as you can see, this is a reversed binary tree. 4 was the right subtree, and now it is the left subtree. 6 was the right subtree, and now it is the left subtree, and so on and so forth. So you see, basically, deep does the DFS over all of the sub-expressions and keeps applying the rule, deeper and deeper. And that way, for example, you can do this kind of stuff. So 41 UA, thank you so much for 2 months of tier 1 subscription. Thank you, thank you, thank you. Can you just define... Okay, so this is a good question. Just a second. Oh, shit. Did I didn't mean to time you out, I'm sorry. I'm sorry, shit, fuck, damn. It's just like, yeah, there we go, I didn't time you out. I was trying to select your message and I missed it, unfortunately. Right, so the message was basically about using equals in the rules themselves, right, or something like that. Here's the thing. I really apologize that I accidentally timed you out. I didn't mean to. I'm sorry. Right, so I just like accidentally clicked something. So you cannot use equals in expressions right now. There is such token as equals, right? There is such token, but there is no such operator. It is purely reserved for defining rules. Maybe in the future we're going to allow using that, especially when we introduce like custom operators and stuff like that, but not right now. Right, so I basically wanted to comment on that. I'm really sorry for banning you. I already unbanned you. So, yeah. So yeah, that's basically everything I wanted to say about this entire thing. And I want you to start working on applying reversed rules, right? So we need to be able to actually get rid of these duplicates, right? and just like define a single rule, and you can apply this rule however you want. What I'm thinking is that maybe we can introduce like a keyword reverse, right? And when you apply the rule, we look for either a symbol, right, the name of the rule, or keyword rule for applying anonymous rules, right, and or keyword reverse for applying any of the rules, right, anonymous and non-anonymous rules, but in reverse, right? So that's basically what we're looking for in here. In Prolog, you can use all operators as symbols, as far as I know, so I know it's possible. What exactly? Yeah, probably. Okay. All right. So let's take a look. And by the way, this entire thing is implemented in Rust, of course. So apply reversed rules. So let's actually go into the Lexa, and we have a bunch of keywords in here. So we have rule, shape, apply, done, undo, and quit. All right, so we probably need to introduce a reverse keyword. I don't know if it's gonna break the compilation at some point anywhere. Let's actually see. So I'm gonna do cargo build, or at least throw some sort of a warning. Okay. So here we have reverse, and I'm gonna, yeah, so basically this is a display interface for the token kind, right, when we try to print a specific token, and this one is gonna be a reverse. Right. So we'll try to compile that. That seems to be compiling, even though it is not particularly correct, because for the keywords we also have a special function, right, that parses the keyword. I do remember that. Yeah, there we go. So this one does not really work correctly, right? So we have to do reverse, and then this one has to be equal sum token kind reverse. There we go. So it will be probably nice to also align everything by equals greater, and there we go. So everything is aligned, everything is nice and perfect. So now let me actually experiment with this entire thing. So let's take a very simple, you know, expression, so to speak, right? So this is going to be a fn main, and let's define apply all reverse rule a plus b equal b plus a. Right, so let's just take this string, take the characters of that string, and construct a Lexa out of that. Right, the Lexa accepts iterator over characters and the file name from which file it was loaded. Since we don't have any file name, we can provide none, right? So the file name can be missing. And Lexa is also iterator, so you can quite easily do token in, and it will actually iterate through all the tokens of the Lexa, and you can print them and just look at them and see how everything is tokenized. And then we can just say cargo run, and let's take a look at the things. So unfortunately token is not printable, but it's debuggable. We can print as a debug thingy. And there we go. Here are the tokens of that string. Right, so here's the string, apply all reversed rule, blah, blah, blah. So apply is a keyword apply, all is identifier, reverse is the keyword. Right, so we were trying to introduce a new keyword, and by the Lexa it was recognized as the keyword, which is perfect. So this is precisely what we want. And this is a sequence of tokens, right? As you can see, I'm not using any third-party like tokenizer, parser, library. I'm just like making everything myself. And this is basically my code, right? So we have a separate module that is responsible for the tokenization, lexing, and stuff like that. And I suppose another thing that we probably need to update is the Emacs support, right? Because right now, right, in Emacs, so here I probably want to use some assoc, but here I want to have a reverse, and since reverse is a keyword, I would like to highlight this entire thing. And of course here we also want to do something like reverse, right? So we need to introduce like a new keyword. I don't understand how to write normal Lexa parser. I can only do parser combinators. What's interesting is that I'm using Recursive Descent technically I'm using Recursive Descent. Recursive Descent. I hope I spelled it correctly. And Recursive Descent is basically parser combinators, or I would say parser combinators are glorified recursive descent. So basically parser combinators are sort of like adapting recursive descent into the interface of a monad, so to speak. Right. So if you know how to use parser combinators, you can quite easily learn recursive descent. And with the recursive descent, you can basically parse pretty much the same stuff as you can with parser combinators. And if you try to just parse anything with parser combinators quite quickly, you will come to a conclusion that it is a pain in the ass to clean up all of the white spaces between the basically tokens that you care about. Right. So essentially, you have stuff like A plus B multiplied by C minus FAB. So this is basically one expression. But you can put a space in here and it's going to be the same expression. You can put space in here, and it's going to be the same expression. And if you try to use recursive descent to parse any of such expressions with any spaces between these tokens, it will drive you insane. Right, quite quickly you will realize that you need some sort of pre-processing step to remove all of these white spaces, or if you don't have any of these white spaces, at least like separate these significant tokens between each other and run the parsing process over these tokens rather than sequence of characters. Because if you do over sequence of characters, these spaces will drive you nuts. And this pre-processing step is basically lexing. Believe it or not, lexing is just basically extracting these significant tokens that you care about so you don't go insane while trying to parse your expression. So that's basically what it is. It's like actually very straightforward. There is like a very specific technical reason for lexing. And if you try to implement parsing without lexing, you will quickly discover lexing yourself. Like you don't even need to read anything about it. Just try to do that without lexing. You will instantly understand why people lex things. Instantly, because it's fucking hard. Lexing is taking a string of characters and turning them into a string of something that is not quite characters, from what I understand. Yeah, I understand it as basically grouping important characters into groups and associating class with that group, right? So, for instance, if I have something, I don't know, foo plus bar, right? I know that significant sequence of characters are this, 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 and this, right? And each of these groups of characters have their own class. This one is open parent. This one is identifier. This one is plus. This one is another identifier. And this one is close parent, right? So as you can see, I identified significant sequence of characters and also classified them. And this information about grouping and classification then used by the parser, right? So the parser doesn't know anything about specific characters. It looks at these things, right? So it has a stream of classes. What's the difference between lexing and tokenizing? There are synonyms, Cinnabons. There are Cinnabons. Lexing and tokenizers are tasty Cinnabons. Okay. So, now. Alrighty. So I want you to add highlighting support for the keyword reverse. So let me go into the editor, and here is the list of the keywords, right? So we have rule, shape, apply, done, quit, and undo. So we're gonna have a reverse. Okay, so after that, I think I need to copy the knock mod into folder with all of the custom mods that I have, and I need to restart Emacs, right? I need to restart my operating system. Okay. And if I try to open square of sum, as you can see now, reverse is highlighted, right? So there we go. So now it's not only a keyword on the level of the interpreter, it's also a keyword on the level of the support for the text editor. So now I can clearly see that something is reversed. Okay, so let me see how we can do all of that. So when you are applying a particular rule, right? So it's probably somewhere token kind apply, right? So there you go. This is a function that processes a command, right? So essentially this function is called every time you press enter in the repo, right? rel wrap, right? So we have to wait for some reason, I don't know why, but let's wait. So I start the process, right? I typed in a command and I press enter. Every time I press enter, this function is called, right? And the input is lexed, basically tokenized, and the lexer for the input is a parameter in here, right? Every time I press enter, this function is called, and now I have the tokens over the input. So the first thing I do, I get the token, right? I pull the first token and I look at that token, what it is. If it's a rule, right, that means I expect a rule definition. If it's a shape, I'm starting the shaping process. If it's apply, I'm trying to apply a rule. And this is probably where we have to, do all of the work. So we can only apply if there is any shaping process in place. Whether we currently have any shaping is defined by current expression, which is option expression, right? And if we do have a current expression, we pull in the next token and we expect identifier. An identifier defines the strategy name, right? It defines the strategy name. So basically it's a number or the, identifier all or deep or stuff like that. So it doesn't really matter. Then after the strategy, we expect other things. We expect either identifier, another identifier, which is the name of the rule we're applying, or a keyword rule, right? We expect a keyword rule to define anonymous rule, right? And now we have to introduce another one, right? So we need to introduce token kind reverse, right? So the rule that we can apply actually can start with either identifier, rule, or reverse, right? So that's basically what it is. What's interesting is that after reverse, we can also have either identifier or a rule. That's what's interesting about that. So how do we even do that? So probably we need to extract, sort of like parsing the rule parameter into a separate function, if you know what I mean, right? So we need to move it into a separate function. So let me try to do that. So this one is going to be something like this. It accepts the lexer. Lexer has this really weird type, right? So it's a lexer and it's also parameterized by iterator, that is iterator over a character, right? So it's pretty abstract type, but it is what it is and it isn't what it isn't. Right, so that's what we have. So, and then this is basically a thing that parses rule parameter, right? So maybe we should call it parse apply rule parameter, right? Maybe we should call it something like a parse applied rule, right? And what this thing should return, it should return the rule, right? So it should return the rule. And the thing here is that rule can be either anonymous or it could be predefined somewhere. Also, there could be error, right? So that means we have to wrap it in result, right? So this is going to be something like this. So this thing is not implemented yet, so we're going to just do it like that. Interestingly, since the rule can be predefined, the predefined rules are defined within the context, so we have to actually get the context by the reference, right? So it's a part of the context in here. Cool. Now, I suppose I need to move this entire thing. So here we sort of define what rule we're gonna have. Oh my god, Leeds Oliver, thank you so much for 5 tier 1 subs. Thank you, thank you, thank you. Like, you didn't really have to, right? Because I don't get any money anyway, right? So Twitch doesn't pay me, but I really appreciate that. So for the subscription, you at least get the emotes and also automatic access to the Discord server, right? So at least that's something that you have. But I personally don't get any money because Twitch doesn't pay me. Can you make rule 110? No, finally somebody asked that. Yes, yes. Somebody asked this question. I don't think, not yet. We don't have a conditional matching of rules. Right, so this is the problem. Thank you so much, Eddie the Coder. Because technically, you can do some shit like, let's say, oh fuck. So I probably need to actually stash whatever I have so I can at least compile it. Not right now. You can't really do rule 110, but I do plan to actually add support for that in the future. Let me show you. So we have to wait a little bit, it's Rust. So you can try to do stuff like 0 plus 1 plus 0 plus 0 plus 1. And basically this sequence of things denote the state of the cellular automaton. I forgot how to pronounce that word again, but anyway. Right, and you can probably define some rules that look like A, B plus C plus rest, right? Something like that. And based on whether something is 0, something is 1, and something is 0, you can say that, okay, so the next value here is gonna be something like, you know, 0. I don't know for sure, but you can kind of do rules like that, right? So you can always match the rest, and then you have to define essentially 8 rules, right? 2 to the power of 3 is 8, and you have to define 8 rules. Then you have to somehow conditionally apply different 8 rules depending on whether it matches or not, right? So you need some sort of a strategy, some sort of a process that, given these 8 rules, will sequentially try to apply them and stop if one of them applies and move on to the next sub-branch and try to do the same process. Once you have such strategy, somehow this system will become Turing complete, right? So you can already define state of the rule 110. You can already define transformation rules. You can't really start the process unless you do that manually. You can kind of do that manually and specifically say that this nth match, replace it with that, but it's not particularly convenient. You need some sort of like a conditional matching, conditional substitution. And I'm not really sure how to implement that yet syntactically and semantically, but I'm thinking towards that anyway. You see what I mean? So yeah, and of course you can define list not only like that. There's a lot of ways to define a list. You can define a list like, I don't know, cons, right? So 0. So it's more of a, like a Lisp-ish way of doing that. You see what I mean? You can define it like that, or you can define it as sequence of applications, right? You can do it like that as well. So this is a valid expression, by the way. So here you have a list that is applied to 0, and then the application of 0 is applied to 0, and application of 0 to application of 0 is applied to 1, and you can actually shape this entire thing. It is a correct thing. I think you have to actually stop in here, and there it goes. You can see this is a correct expression, believe it or not. You can, for example, match, right? So by doing F and then this, you match everything and ignore the argument in here. So this will effectively remove this argument, right? So we have to do something like maybe all. Yeah, you have to do something like this. Yeah, there we go. So, and if you keep applying, you basically remove sort of element from the list until you're left with the list. So there's a lot of ways to define list, right? You have an AST over the expression. However you form this AST, you can have different data structures, right? So at the moment you apply only patterns match based on operators? No, I apply patterns based on anything. Anything. I mean, I don't know, like for instance, you can do shape f a plus b, right? So, and then you can apply a rule to all where you take, you can actually ignore f and then you take a plus b and you say that this becomes ab. Right, so you pattern match the whole application, and this thing should become A applied to B, and it became. Right, you can pattern match any sub-expression of AST. So pattern is just an expression, and it can match any other expression, like any other, like anything, if that's what you mean. So underscore is basically a special variable that ignores whatever it matches. Try making Y combinator in Nock. I forgot what is a Y combinator. Like Y combinator implies. Wait a second. Y combinator. Let me remember. I know it's a thing that applies. I hate this company. This company poisoned any searches, like any web searches. Like holy fucking shit. How am I supposed to search for a Y combinator? Yeah, for fixed point combinator, I suppose, right? Thank you so much. So it's a function that essentially, so it takes a function. I'll think how can you express this kind of stuff in Nock, because Nock is not a lambda calculus system, right? It's not a lambda calculus system. So I need to think how I can translate lambda calculus into Nock. You can think about it like yourself, right? You can treat it as a homework as well. But yeah, thank you. Thank you for interesting idea. I will see how we can do that. It would be pretty cool to add that to the examples, right? So here you can do Y combinator. So there is no lambda functions in Nock, right? It's just like you have AST expressions and that's it. That's basically it. Okay, so let's actually go back. So I need to pop this entire thing. So I had some. So this is right. Yeah. There we go. Cool. So let me try to compile whatever we have. So read from disk. Okay. So what I needed to do, right? What I needed to do is parse rule, right? So parse rule. So what I wanted to take this entire expression, right? So I'm taking this entire expression and I'm pasting it in here, right? So I'm pasting it in here. So expected tokens, we specifically expect identifier or rule, right? We can kind of try to implement it in terms of itself, right? So this thing will first see if it starts with the reverse, right? And if it starts with the reverse, it's gonna call itself again. So that way you'll be able to apply a specific rule, right? Rule 1, you can apply it as a reversed, but then you can apply it as reversed to reversed. So that means that you will apply it as the regular one. I kind of like this idea, so let's actually do that. Okay, so what I can do is maybe I can just like peek into the next Lexa. Right, so this is going to be Lexa peek token, right? So I'm going to pick token and maybe I'm going to clone it because why not, right? So I want to have this token. or maybe not. So let's actually not clone it yet. Let's not clone it yet. And let's match the token kind, right? If the token kind starts with the reverse, right? If it's, why does it say reversed? I don't really remember having reversed yet. It's just called reverse. It's just Emacs trying to do this kind of stuff. So if we encounter reverse, what I do is that I drop the token, right? So this is going to be next token, right? I just straight up drop this entire thing. And then I want to return essentially self parse applied rule. This one is interesting. So I do that. So this is Alexa, right? And here I need to get the rule from that. And what I'm going to return a reversed rule. So I need to construct a new rule where head is equal to the body and the body is equal to the head. So that's basically what this. That's pretty cool. But I think a rule also has other things. It also has the location. And location here is going to be, I think, token location, right? And because of that, I think we have to clone this token, right? So we're going to be cloning this token, right? And interestingly enough, I think we can straight up say next because we're going to be consuming it nonetheless, right? So we're going to be consuming it nonetheless. All right, that's fine. That is totally fine. All right, so the next thing we can have in here, right? If it is a rule, that means we're trying to construct an anonymous rule, right? So that's what we're trying to do. We're trying to construct an anonymous rule. And when we're trying to construct an anonymous rule, we need to first parse the head, right? So we're going to do head self parse Alexa, right? So we have a head. Then we expect the equals, right? So we're going to say expect the token Alexa token kind set. Oh yeah, this one is rather interesting. I have basically a special type called token kind set, which encodes several token kinds, right? So there's a token kind, for instance, identifier, or maybe token kind, I don't know, plus, right? And if I want to say, okay, I mean either identifier or plus, I can put them together as a token set. And under the hood, token kind set is in fact just a bit mask, right? Token kind set, right? So if you take a look, token kind set inner type is U64, and when you add any token kinds in here, it like basically sets the bits and stuff like that. And that way you can pass several token kinds as like a single number. And it's pretty convenient because then you can generate interesting diagnostic messages, right? So for instance, if you try to print a token kind set, it will actually print the names of the token kinds. It will separate them with commas, and at the end it will add or if it's needed, right? So you can say expected either that, or that by just like specifying token kind sets as a single parameter, right? So it's pretty convenient to generate like different diagnostic messages and stuff like that, at least for now. I'm not sure if I'm going to keep that, but it is like that for now. And it's pretty convenient to pass it to the function that expects a certain token, right? So you can say I expect one token, or I expect either that token or that token, right? And you can basically, you know, put that in a set where you can have empty set, and you can then say, okay, I expect token kind equals, right? So, but it's not particularly convenient. You can actually say that it consists of a single element in here, right? So this is basically what I have in here. And if the next token is not equals, it will basically throw an error. So the next thing we need to do, we need to parse the body, right? So here we're parsing the body, and there you go. We have we parsed a rule, an anonymous rule, which we can put in here. So we have a head and body. There we go. We have a rule. Pretty cool. So And probably we also need to wrap all of that in OK, because the result of this function is result. So we have to do something like that. There we go. And if the next token is an identifier, right? So if it's an identifier, that means it's a name for a specific token, right? So that means we're going to try to get that name, right? We're going to try to get that name. We're going to try to get that name, and if it does not exist, we're going to say it does not exist, and here we can actually clone this entire thing, and that's pretty much it. We do a little bit of a cloning, but I think it's okay for now. I'm not trying to be like super efficient, right? I'm just trying to be working, at least, right? So in here we don't really need to return anything. Okay, so parse applied rule. So that should actually support the reversed syntax, if you know what I mean. Right. It should support the reversed syntax. Okay, so let me see. So what do we have in here? So we have to go through this kind of stuff. So operator apply cannot be applied to values that implement try. Okay, so here we don't really have to do that. That's cool. So supplied one argument, parse applied rule. So it means it has to be self. And does this thing modify? I don't think it modifies anything, so we can do it like that. Okay. So so this one has to be self parse. Self parse. So, and since parse modifies the context, right? Since it modifies the context, I suppose we have to make it mutable. Though, wait a second, I think I'm an idiot. Because here we're trying to parse an expression. Okay, we're trying to parse the expression, so here we have that, and the location. Okay, so the location is going to be lock token lock as well, right? Though, interestingly, we can... Yeah, I think we're gonna use location of this thing from the reversed thingy. Okay, so here, expected strict rule, but found rule. Even though I tried to clone it, which is rather strange. Like, why didn't you allow me to clone it? I would expect that clone will just return. So do I have to like do it like that? So non-exhaustive pattern match. Okay, so in here we can try to now do the following thing, right? So this is going to be error unexpected token. So in here we expect a token kind set. So single token kind reverse set token token kind rule set token kind ident, right? So this is what we expect, but what we've got, right? So what we've got is going to be the token, right? So that's what we're going to have. All right, so is it working? Move occurs, which does not implement copy. I'm not sure what's up with this thing. Honestly, I'm just like not sure why it doesn't want to clone properly. So this thing will return a reference to rule, right? So in here we have just a reference. I don't understand why can't I just clone this thing. So can anybody tell me, like, what's up with that? Is that because of this? What does it want from me? No method clone in the current scope. Oh, rule is not clonable apparently. I thought it's clonable. Why is it not clonable? I forgot to make it clonable. Right. Okay, so that explains it. That also explains why. Right. So, and after that, I don't even have to do this kind of stuff. Was it actually explaining me that? That's pretty weird. Ah, really? Nice language, by the way. It wasn't even explaining me that I have to make it clonable. Like, if I remove clone in here, does it even say me anything? It doesn't even say me that I have to make it clonable. Look at that. Look at that beautiful, intuitive language. Of course. Right. So, nice. Nice language, by the way. Thank you. Thank you very much. Okay. So, now let me see. So if I go to implementation of the context, right? And so essentially here now I can do the following thing, right? I can just self, maybe not self, but parse applied rule, and I can provide the Lexa. Right, there we go. So this to do is actually quite useful, right? So I'm going to keep it in here. Okay, so here is the rule that we're trying to apply, right? And that should be it, actually, believe it or not. That should be literally it. So, okay, good. Seems to be working. Seems to be working. Okay, so let me now try to run the entire thing. Rel wrap. So, and let's go to the square of sum. Let's start shaping a plus b, right? So I probably need to define the rule square a2 equal aa, right? So here's the rule, and if I try to apply the square rule to everything, this is what I get. If I try to apply the reversed rule, it gets back. That's pretty cool. So yeah, I apply the reversed rule. So reversed rule does not apply again, but because of how I define this thing, I can actually apply reversed rule, which is the original rule. So I made the parameter of apply strategy recursive, right? So the applied rule is either applied rule or reversed applied rule. And since it's a recursive definition, you can actually reverse this entire thing. It's absolutely unnecessary, by the way. It's absolutely unnecessary, but I decided to do that because I like it, because it's dank, right? So it's sort of like a recursive grammatic. So yeah, it's absolutely dumb, but I mean, it works. So this way, you don't have to define, you know, the redundant rules, right? Redundant rules that don't do anything. So we can even remove all of them, right? So now we have only literally 5 rules, and we use these 5 rules to demonstrate that a plus b squared is equal to, you know, the known formula. We can try to now run this entire thing. I'm gonna run it on square of sum, and as you can see, it still works. So yeah, that's pretty cool. Can you make rules depend on other rules? This is a very good question. This is a very good question. Okay, so here's the interesting thing. We can actually replace A and B with anything, right? For instance, we can say it's C and D, right? And if you run it, it still basically converges to the same thing, right? So these specific arguments don't matter. They don't matter so much that you can even have sub-expressions in here, right? So we can have g of b, right? And at the end of the day, it will still work, right? Instead of a and b, you have f of a and g of b, and it still like works. What's interesting is that you can have free variables instead of these parameters. You can have free variables. There we go. Look at that. So these are not just symbols. These are variables. So by implementing this sequence of applications, you sort of proved demonstrated that this, right, that this is equal to this. So you have all of the moral rights, so to speak, to define a rule that says, let's call it square of sum, right? You can define such rule and then use this rule in other shaping, right? So any shaping defines the head, sort of defines the head, and at the end it defines the body, the final sort of shape of the expression. So why not just allow you to do this kind of stuff automatically? So in the future, I plan to have this syntax. So you start a rule, you give the name of the rule, and you start a shaping. And the beginning, so the first expression of the shaping becomes the head of the rule, and then the final expression becomes the body of the rule. And that way you define a new rule that you can use in other shapings that become other rules, that can be used in other shaping that also becomes rules. You see what I mean? So it doesn't work right now, but this is like ultimate plan. Isn't it cool? Isn't it cool? So anyway, what's interesting is that you can also define rules while doing the shaping. So you can do apply all, and then you can have anonymous rule, right? So you can have something like a plus b equal b plus a. So this is an anonymous rule. As you can see, it doesn't have a name. You can just apply it in place and that rule ceases to exist. What's interesting is that who said that I cannot use the same syntax for defining such rule? What if I want to apply all rule and start shaping that rule? I don't really know how that rule is going to look like, but I'm going to start shaping it, right? So I'm starting shaping it, and I just apply some stuff in here, right? Then I'm done shaping it, and then it defines a new rule that get immediately applied to upper expression. So you can have like a nested shapings that define rules and other shapings and so on and so forth. So this entire thing can be very much recursive. Yeah, you can go crazy with this kind of stuff. None of that is implemented yet, by the way, but I plan to have this like very much like recursive nested nature of the language, where rules can be used in shapes, and shaping can be used to define new rules that can be used in shapes that define other rules, and so on and so forth. Right. What's funny is that, you know what's cool? Is that none of that was planned when I started this project. I sort of discovered this entire thing. I sort of discovered this recursive nature of rules and shapes. Like, I never planned this to be like that. I just wanted to have rules that pattern match things and a process of applying these rules. That's the only thing I needed. And then I kind of discovered that you can actually like interleave these two processes together. Like, I never thought about it, but as I were implementing it, like I discovered that, well, that's actually pretty cool. So maybe I'm going to implement that. So yeah, syntactically it looks like shit, of course. But maybe in the future I'm going to actually make syntax a little bit better, right? So for now it is like that, but yeah. So what I'm focusing right now is just like semantic. And semantic, I almost nailed the semantic, I gotta say. I almost nailed the semantic. Anyways, okay. So let me see if I didn't break anything. Right, so I broke something, yeah. Okay, so as you can see, it seems to be working, it seems to be twerking. It will be also pretty cool to try to sort of expand a minus b squared. How is it going to look like? That would be actually pretty cool. So basically we have a square of sum, and what about square of difference? Right. So as far as I know, square of difference is a squared minus 2ab plus b squared. But you have to prove that, right? How would you prove that? Okay, so let me just double check that everything works as I expect. And I would like to actually move square of sum to the examples, right? So let's actually move it to the examples. Right, we have quite a few things in here, actually. I really like that. Droka87, thank you so much for Twitch Prime subscription. Thank you, thank you, thank you. If I missed any one subscriptions, I really apologize. Like, I just I think I didn't. Gia Films, thank you so much. 41 UA, thank you, thank you, thank you. All right, but if I missed anyone, really, really apologize. So here are the piano numbers and stuff like that. So even though this entire system sort of like moves towards being Turing complete, I do not intend it to be a proper programming language, right? So it can be a proper programming language, but it's completely accidental. What it is just like a environment to play with math. That's basically what it is. Nothing particularly special. A rule of arbitrary positive integer power using induction. Arbitrary positive integer power. I don't know what it is. I'm not sure. It's like MATLAB. No, I don't think it's like MATLAB. Again, whatever MATLAB is doing is actually too high level for what we're trying to do. We're not just doing math, because math is a very broad thing, just like programming. When you say when you're a programmer, that you are a programmer, what do you mean? Do you mean like a low-level hardcore, like a game engine programmer, or do you mean just a front-end web developer who primarily doing CSS all day? Like when you say programmer, what do you mean? What is programming in 2022? It's a very broad thing, right? Extremely broad thing. Math is as broad as programming today. When you say math, what do you really mean? Here we're doing a very low-level math. Again, it is a very low-level math where even numbers are not defined. You have tools to define numbers, but they're not defined. So usually people start learning math from arithmetics, where numbers and operations on numbers are kind of defined, at least integers. But we're even lower than that. We don't even have numbers defined. So you kind of start with like a set theory. I'm not sure even if we even have sets defined. How many people complained about the equation? I don't know, I didn't count. How do you like my title, by the way, chat? Do you like it? Right. It's cool for it to be low level, but wouldn't make it less practical? I don't think so. First of all, I was making it for myself, right? Because I usually do this kind of stuff on paper. Believe it or not, from time to time, I like to just do these mathematical transformations myself on a paper for recreational purposes. Yes, I am weird like that. I'm really sorry. But I like to do this kind of stuff like on my own recreationally. And what I notice is that I'm pretty dumb. And I quite quickly make a lot of mistakes that lead to a complete gibberish. And I tried to improve myself, but I couldn't. I'm too dumb for that. So what I decided to do, I decided to make a program that can do these transformations reliably. So, and the only thing I need to do, I just need to define the rules and just apply the transformations. But whether it's practical or not, I really don't care. It's just like something that I want to have for myself. This is the system that I always wanted to have. The closest thing to that is Coq, but it's very cryptic and very mathy, and like it's just, it's more of a for people who are doing math professionally, right? Coq is a very professional, very complex tool for me. So I want you to something like close down to earth. Just like you have an expression, you can pattern match that expression and transform it. That's what I wanted to have. And that's what I made. So whether it's practical or not, I don't know. I'm going to use it. I'm going to be the one who's using it. And it's open source. If you want to make it practical and use it for your own thing, feel free to do that. It's under MIT. So it's like open for everyone. It's cool to do math recreational. Like I never managed to go deep into recreational math precisely because I'm too dumb and make a lot of mistakes while I transform equations and expressions and stuff like that. Like I very easily make mistakes and it's just so frustrating. Yeah, so hopefully this tool will help me to just go a little bit deeper into recreational math. We'll see. Okay, so now we can apply reverse stuff. I think okay, so we have a square of sum. So let's do a committee. By the way, I think I need to first also remove the to-do, right, about this kind of thing. So apply and reversed. Implement replace macro. This one is actually very interesting. I don't know if we'll have time to implement that today, but yeah. Okay. Implement reversed application. Rather, application of reversed rules, right? Because first you apply, and then you say whether you apply a reversed rule or not reversed rule, right? So that's what you do. Okay, I'm gonna push that right into the repo. You can find the source code of this thing in here in the chat. If you're watching on YouTube, you can find that in the description. If I ever upload this thing to YouTube, because I still don't have motivation to do that, because after the start of the war, I was extremely depressed to the point that I couldn't program for a month, right? So I only recently started to go back to that. So, oh man, I wish it's over soon. It's like so many people are dying. Holy shit. So anyway, what I wanted to do, I wanted to try to. Are you Ukrainian? I'm not, but I have a lot of, like, I know a lot of people from Ukraine, and it's actually making me really, really anxious for them. Are you living in Russia? Yes, I am living in Russia right now, and it's fucking insane. It's fucking crazy to like wake up one day and realize that you're living in literally fascist state. It's just like I wouldn't even know that it is like that. It's really, really fucking strange. So, it is what it is, and it isn't what it isn't. Do you think this could be ported to something like C or C++, C#? Of course it could be. Yeah, of course, why not? It is amazing to see you. Thank you. Thank you. There is no problem importing that to C or C++ or C#. In fact, I was originally planning to implement that in C, but I decided to do that in Rust because I wanted to use Rust as an opportunity to attract more people to my streams, right? And for me, it is important to attract more people to my streams because the more people watching me, the more people will eventually use the donate command that is in the title, right? So it increases the chance of people triggering the donate command, which is a good cause, I think, right? So that's basically the idea. That's literally the reason why I'm using Rust. So that's literally the reason. But originally I wanted to use C. Okay. So let's actually try to prove, or at least demonstrate, what a minus b squared is equal to. Right. So let's give it a try. So I suppose I can just grab some rules from the square of sum and just like reuse them. Yeah, I definitely need to develop a system that allows me to like move these things into a separate library that I can load up in a repo or something like that. And that will be useful because I don't really want to redefine these things every time, right? You want to put that in a standard library somewhere. You can take kilometers from where I'm depressed for a month. Go 21st February 4 a.m. after 2 days. So where is my old coding project? Yeah. I hope you're staying safe. So as far as I know, you're in like Kharkiv region right now, right? But you're not in Kharkiv directly, right? So hope you're staying safe there. All right. So let me reuse some of these rules. right? So redefinition of existing rule, so it already exists. So that means I want to try to apply the square rule in here. There we go. So this is what we got. We don't really have sort of like a redistribution for the subtraction. So everything is quite in the middle of nowhere. Okay, that's cool. Rope Mark D, thank you so much for 50 rate. Thank you. Thank you for rating me with 50 open tabs. That's quite a lot of tabs. Thank you, thank you, thank you. All right, so yeah, let me see. So we want to have some sort of a rule where you have A multiplied by B minus C. And obviously this is equal to A multiplied by B minus A multiplied by C. So it's sort of like a distribution over multiplication and subtraction, right? So that's what it is. So there we go. And I can try to apply that multiplication and subtraction. There we go. So this is what we have in here. So that's pretty cool. So which is something that we can probably use at some point. All right. And I also need multiplication commutativity, right? So let's actually apply all commutativity. Yeah. Apply all right, there we go. And it actually swapped around both of these things, which means I can apply this thing yet again, right? So I can apply all distribution like that, and this is what we got, right? This is what we've got, which is very interesting. So how we're gonna be transforming all of that. So first of all, we can actually take this, like A multiplied by A and B multiplied by E, right? So apply all square, right? So, but it's not going to work, so we have to sort of reverse it, right? We apply all reverse square, and as you can see, we're using the same rule, but it's just like this. And the question is, like, we have to reorganize the parentheses. We have to reorganize the parentheses. So we have something like A minus B minus C, right? So what you're going to end up with? So you're going to end up with probably plus B minus C, but the stuff is actually looks like this, right? So I think this is what we have to do in here. Yeah. Because how our parser works, it's sort of like a right associative, right? I think that's what it is. It's a right associative, right? Because it's going to put the parentheses like this if it encounters the operators of the same precedence, and plus and minus have the same precedence, right? So because of that, to actually make it work, I have to put parentheses in here, right? I have to put parentheses in here. So A minus B plus C, but it's going to be tokenized like that. If I do something like this, right, without parentheses, it will be automatically parsed like this, which is not correct, is it? I don't think it is correct. Is it correct? I think it is correct. No, it is not correct. Right. So because of that, what I have to do is A minus B, right, minus B plus C, but I also have to explicitly do something like this. Okay. A plus C minus B. That's already better, actually. A plus C minus B. Right. Yeah, that's already better. So we can use that. And maybe it will even maybe properly make it. Let's actually try to apply this rule as an anonymous rule, because I don't know how to name that rule. Right, so I'm going to try to apply it like this. And yeah, that kind of worked, I think. But unfortunately, Right, unfortunately, it moved this thing further away from that one, right? Which is not ideal, right? It is not ideal. So let's actually do undo. And let's try to do the thing the way I want it to do, right? So let me try to finally do it the way I want it to do it. All right, so, okay. So, and that way, oh, that's actually pretty cool. Because I can try to apply it yet again. I'm pretty sure I can try to apply it yet again. But it actually has to be reversed. Oh, shit. So that means I have to do it. Wait a second. This one is a different rule. This one is already a different rule. Okay. So this one this time is something like this. Right. So and how are we gonna be doing all of that? I suppose we can quite easily say that this is A minus B plus C, right? Yeah, we can actually say that. Yeah, I think. Can we? Can we say that? We don't have to reverse that, but all right. And then I can essentially apply multiplication commutativity to which one? I think that, God damn it. That one, right? And then, do I have this rule somewhere? Right, so double sum, I can define double sum, apply to the first one double sum, right? And I think I did it. Cool. Did I demonstrate that? I think I did demonstrate that. So, yes. That's why you have to prove everything in code. No. This is why I created knock, right? This is literally the reason why I created knock, so I don't have to prove everything. Okay, so yeah, that's pretty cool. You can probably sort of like demonstrate other expressions, right? So maybe a plus b cubed, right? So it's a plus b cubed. But that's a more complex expression, right? So it's a way more complex expression. Okay, go. So, and then we can say done. It would be also kind of cool to have an ability to save the current session to a file. You know what I mean? So you just basically did some doodling around and say save to file, and then you can edit that file and maybe clean it up and stuff like that. That would be also kind of cool. And I think I even created a do for that, right? Okay, so for how long am I streaming already? I don't know, I have like a less than half of an hour, and I don't think I'm gonna be able to do anything within the half of an hour. So does anyone have any questions maybe? Does anyone have any questions? About this entire thing, you can find the source code of this thing in here, right? And for people who are watching on YouTube, you can find it in the description. Do you have any questions about this thing before I go? Can you quickly demo the project? I already did at the beginning of the stream. Can you quickly go over a knock? I can do. I already did at the beginning of the stream. So there's a way to print the history of rules applied to the shape. There is no way to save. Like right now, the REPL doesn't save anything, but we can just introduce that at some point, right? So sometimes, the thing is, sometimes we apply the defined rules, sometimes we apply anonymous rules that are not defined. We also have to distinguish between those, right? And that's kind of a, yeah, that will require a little bit of a thinking. This language is rather interesting because it's intended to be interactive, right? So it's intended to be worked with in a repo, right? And because of that, this fact kind of affected the syntax of the language. That's why it's very Pascalish, so to speak. Right, so let me show you square. Right, so it's very Pascalish because it's like each line is meant to be a command in a repo, right? So, and it's easier to type such commands like this, though maybe apply is not particularly like necessary word, right? It is not particularly necessary word, so yeah. There will be something like standard library. Yes, there will be, of course. All right, so I guess that's it for today. I hope today's stream was interesting. So thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all next time, right? So I'm gonna keep working on this thing off screen. I'm gonna keep adding things, and if I encounter something interesting, of course I'm gonna do another stream where I'm gonna demo this entire stuff. In the future, we're definitely gonna be able to do more interesting and cool stuff with this language, right? It's already kind of cool, right? So we already can do a lot of things, but I definitely want to have custom operators, right? So that would be kind of cool. All right, so thanks everyone for watching. Love you all. Stay safe.